Welcome back. We are now moving on to section 12.3, rate laws. In this section, we are going to explain the form and function of a rate law, use rate laws to calculate reaction rates, and use rate and concentration data to identify reaction orders and derive rate laws. So rate is directly related to reactant concentration. Rate laws or rate equations are mathematical expressions that describe the relationship between the rate of a reaction and the concentration of its reactants. For example, a generic reaction, you have some A reacting with B to form some products. When it comes to rate law, we don't care about the products, we only care about our reactants. And A and B, again, are stoichiometric coefficients, just like we've seen before. A generic rate law looks something like this. The rate of the reaction is equal to some constant K times our concentration of A raised to the M power times the concentration of B to the N power. So K is the reaction constant. Okay, M and N are just our powers. They're the reaction orders. They are exponents specific for each compound. They're generally positive integers, but there are times where they can be fractions, negative, or zero. And we are going to study zero. We're not going to look at fractions or negative rate exponents. So that's what I got to do in grad school. Fun fact. The rate constant K is independent of reaction concentrations, but it does vary with temperature. So doesn't care about reaction concentrations, but it does care about temperature. So your reaction, the rate constant could be different at 50 degrees Celsius versus 100 degrees Celsius, for instance. So those reaction orders tell us the mathematical dependence of the rate on the reaction concentrations. So for instance, here, this reaction is mth order in respect to A and n order in respect to B. So for instance, let's say m equals 1 and n equals 2, then the reaction is first order with respect to A, second order with respect to T, or to B, sorry. The overall reaction order is the sum of the exponents. Okay, so it's m plus n. In this example, it's 1 plus 2, so as an overall reaction order of 3. So different reactions have different rate laws. Stoichiometry doesn't tell us anything about our rate law. For instance, the reaction here, N2O5 becomes 2NO2 plus 1/2 O2. The rate law is the rate is equal to K times the concentration of N2O5. Only reactants appear in a rate law. Okay, this holds true for everything. And K is the rate constant for this reaction. Every different reaction has a different K. So we can use our rate law to calculate an instantaneous rate or an initial rate of reaction when we have specific reaction concentrations. But some reactions have a much more complex rate law, which we will see a little later. Now a little bit more about K. It is specific for a particular reaction at a particular temperature. And again, it is independent of reactant concentration. It has to be determined experimentally. You can't just guess a K, it doesn't just show up. You have to determine it experimentally. Same with determining a rate law for a reaction. You have to do experiments to figure out the rate law. You cannot just use a balanced chemical equation. So the balanced equation tells us nothing about the rate law. It lets us see reaction rates or relative rates, but it does not give us the rate law. So if we have a reaction that only has a single reactant A, so this A becomes products, our starting rate expression is K times concentration of A to the M power, where M is the order of our reaction. We have to determine this experimentally. Again, we cannot get it from balanced equations. That's why it's to the M power, it's not to the A power or anything. It doesn't have anything to do with anything at all. Again, the orders of the reaction tend to be positive integers, 0, 1, 2, but they can be fractions or negative. Now, most reactions involve more than one reactant. So you might have some A and B becoming products. So your generic rate equation is K times A to the M times concentration of B to the N power. And there are three orders to this, like we talked about. M is the order with respect to A, N is the order with respect to B, and the overall order is M plus N. So let's go ahead and look at an example because talking about A's, M's, N's, B's gets a little weird. So let's look at an example. It's a lot easier to visualize. So we're told an experiment shows that the reaction of nitrogen dioxide with carbon monoxide is second order in NO2 and zero order in carbon monoxide at 100 degrees Celsius. And we want to know the rate law for the reaction. So we can start with our generic rate law. The rate is equal to K times our concentration of NO2 to the M power times the concentration of CO to the N power. And we were told for NO2, it's second order. So that means we have K times NO2 to the second power, and CO is zero order. Now anything to the zero power equals 1. So now our rate law simplifies down to K times the concentration of NO2 squared. So this is our rate law at 100 degrees Celsius. You don't need to worry about finding a K. That's something, again, that has to be done experimentally. So leaving it there as just K works great. We're going to look at a problem looking at this map here, looking at some data, but this is just showing some stratospheric ozone concentration in the ozone hole that occurs over Antarctica during its spring months. And then we're going to actually look at some data showing nitrogen monoxide and ozone, which NO, nitrogen oxide, is a big cause of ozone depletion. So we're going to talk about that in an example in a minute. But first, we need to talk about order with respect to a reactant. Like we've already talked about, this gives us the dependence of the reaction rate on the concentration of that particular reactant, like saying this is second order with respect to oxygen, for instance. And then the overall order gives us an understanding of how all the reactants contribute to the rate of a reaction. So at my work in grad school, the stuff I was looking at, I was overall orders of a reaction, because there's so many reactants, I can only look at so much. This also, the overall order is what gives us the units of the rate constant for the reaction. We'll talk about a little later in this section, but the units for K are going to change depending on your order of reaction. One way that we determine the rate law of a reaction is to measure the initial rate, which is the rate of the reaction at time 0. So what we do is we take the initial rate with a number of different initial reactant concentrations. So we go, okay, I'm going to do 3 trials where my concentration of NO stays the same, but I change ozone concentration. And then I'm going to do some trials where I keep ozone the same and I change NO. And then I can use that to determine the rate law. And we're going to look at that in an example, which makes a lot more sense than just words on paper. So like I was saying, Like I was saying, you could experimentally measure the initial rate with each of the two different concentrations for your reactants, and you see how that affects your rate. It's a direct result of each of the reactant when you change it. So when I change NO, for instance, the change in rate is only related to NO. It's not being related to ozone because ozone is constant. There is no change in ozone initial concentrations. Okay, so then you calculate that order, and then you can do the same for your other reactant where you hold it constant and change the other reactant. So you do this with every single reactant till you eventually get your coefficients for the exponents. So let's look at this example. A little bit more. Ozone in the upper atmosphere is depleted when it reacts with nitrogen oxides, NO, or NOx. The rates of the reactions of NOx with ozone are important factors in deciding how significant these reactions are in the formation of the ozone hole over Antarctica. One such reaction is the combination of nitrogen oxide, NO, with ozone, O3, and we're given our reaction. This reaction has been studied in the laboratory, and the following rate data were determined at 25 degrees Celsius. Determine the rate law and the rate constant for the reaction at 25 degrees C. And don't worry, I have this data on the next table. I don't know why it put two x's for the times 10 to the negative 6, but don't worry about that. It just means times 10 to whatever power. So let's look at this table. The first thing we should notice is that the first three trials all keep the same amount of NO. Okay, so here NO is constant. And then the last three, so now these three, have ozone constant. So those are going to be very helpful for us. And let's start by writing our generic rate law. K times the concentration of NO to the M times ozone to the N. So what we can do is compare our rate, the rate of 2. We divide it and we look at how it changes. For this type of problem, we can actually look at it and determine it just kind of looking at the numbers. So let's go ahead and try to find M. So I'm sorry, try to find N. No, sorry. We're going to find M first, where NO is held constant and ozone is different. So that's our first three experiments. And what we can see is our reaction rate changes in proportion to the change in ozone. So let's look at trial 1 to trial 2. So let's say the rate of, we'll do the second divided by the rate of the first. So, and these rate equations, right, are equal to K times NO to the M, O3 to the N. So we have K times NO, and we're going to put, this is from trial 2 to the M, times ozone for trial 2 to the N, divided again by K times NO. Oh, I'm sorry, we're actually determining N here, sorry. From trial 1 to the M times ozone from trial 1 to the N. So we know that K is the same, right? K is a constant, we're at the same temperature, so those go away. We also know that for reaction 2 and reaction 1, our concentration of NO is the same, it's constant, so these guys are going to cancel out. So we're left with the ozones now, with our ratio of ozone at the second concentration divided by the first, and then our rate of 2 divided by our rate of 1. So the rate of reaction 2 we're given right here. This is, oh, sorry, that's for delta NO2, not for delta O. But what we see here is our concentration of ozone doubles. It goes from 3 to 6. So we have 6.00 times 10 to the negative 6 divided by 3.00 times 10 to the negative 6. So that tells us that we have 2 to the n power. And one thing we also know from when we've looked at relative rate laws is looking at the balanced equation, the rate of change of ozone is the same as that of NO. And it's also the same as that of NO2. So 1.32. 13.2 divided by 6.60. So now if we look at this 2 to the n and we look at these relative rates, because we know, again, that delta NO2 over delta T, using stoichiometry and stuff, we know that this is the same as the negative, or it's the rate of decay of delta ozone, delta T. So now we can look at these rates now, since we know they're the same numbers. Rate of 2 is 1.32 times 10 to the negative 4th over 6.60 times 10 to the negative 5th. So this ends up coming out to be just about 2. So 2 to the n is equal to 2. Taking the log of both sides, you get that n is equal to 1. Or just looking at this going, okay, 2 to the 1 power is equal to 2. So now we have our value of n. Okay, you can do this by just kind of looking at what happens to the rate of the reaction, that delta NO2 over delta T, and just kind of go, oh, look, this rate doubles when the concentration doubles. But I like to actually show the math and the thinking behind it. So now let's go ahead and look at our other two to figure out M. So eeny, meeny, miny, mo, let's look at reactions 3 and 4. So we're going to do reaction 4 divided by reaction 3. Okay, the rates of 4 divided by the rate of 3. K equals K times NO2. I'm sorry, not NO2, NO from reaction 4 to the M power. And we know that ozone is to the first power, since we just solved for that. And we also know, though, even if, let's say we decided to look for M first, the ozone we know is kept constant. Those concentrations stayed the same, so those are going to cancel out anyway. The K's cancel out. So same type of thing. Our rate of reaction 4 is equal to 3.96 times 10 to the negative 4th divided by 1.98 times 10 to the negative 4th. And that is equal to our NO concentrations to the M power. So that is now 2.00 times 10 to the negative 6th. And this is to the M power divided by 1.00 times 10 to the negative 6 to the M power. So this simplifies on the right to 2 to the M. So now dividing the left, 3.96 divided by 1.98, we get 2. So 2 is equal to 2 to the M. So M is equal to 1. So now we have our N and we have our M for our reaction. And the last step is to figure out K, because we have experimental data and now we know our rate law exponents. So now our rate law is equal to K times NO to the first times O3 to the first. We don't need to write in those ones. You can just leave it like that. So the last thing to do is pick some of our data and plug it in for the rate, for NO, and for ozone, and solve for K. So simplifying, K is equal to the rate of our reaction divided by the concentration of NO times the concentration of O3. Let's go ahead and use trial 5 because the poor thing just got left out all alone. So the rate of this reaction here is 5.94 times 10 to the negative fourth divided by our concentration of NO, which is 3.00 times 10 to the negative 6 times 9.00 times 10 to the negative 6. You can use literally any data point. It does not matter. This is just me feeling bad for inanimate objects. So we have 5.94 times 10 to the negative fourth power divided by 3 times 10 to the negative sixth and divided by 9 times 10 to the negative 6. And you get a big number. Don't be surprised. You get that K is equal to 2.20 times 10 to the 7th. And let's go ahead and look at some units. So erase some of this. So we know that the units of the rate are equal to moles over liters times seconds, moles per liter per second. And our concentration, these guys are in moles per liter since it's molarity. So we see one set of moles per liter cancel out. So then our units now become liters on top because you have 1 over seconds over moles over liter. So that now we have liters over moles times seconds. So just to rewrite this better, 2.20 times 10 to the 7th liter per mole second, or liters times inverse moles times inverse seconds. That works too. Same thing. So that's how our units work. So then our final rate law is that R equals 2.20 times 10 to the 7th liters per mole second times concentration of NO times the concentration of ozone. Now we've got a rate law and our rate constant. All right, let's take a nice deep breath, exhale, for us to continue on. All right. So this is a good question that would be a great exam question. So this is something that you guys need to be confident in your abilities. All right. Now time for another example. Yay! Very similar to what we just did. This one, we're going to figure out a rate law from initial rates. We were given some experimental data for this balanced equation you see here. And we want to figure out our rate law and rate constant. So first things first, our generic rate law is going to be the concentration of K times NO to the M times Cl2 to the N. So now we need to figure out M and N. So this time let's find M first, which means that NO has to change, but Cl has to stay constant. So that happens in trial 1 and trial 3, where you see NO is both, or I'm sorry, I keep getting those backwards. We want to find M first, meaning Cl has to be the same and NO is changing. Oh, I was right. Don't mind me. NO is changing in 1 and 3, and Cl is the same there at 0.10. So we have the rate of reaction 3 divided by the rate of reaction 1. This ratio is equal to K times NO from reaction 3 to the M times Cl from reaction 3 to the N divided by K times NO from reaction 1 to the M times Cl, or Cl2, from reaction 1 to the N. And we know that the Cl's are the same, so those cancel out. The K's cancel out because they are the same. So now we can go ahead and solve. Now we know our rate from reaction 3 is equal to 0.00675. Divide that by the rate from reaction 1, 0.00300. And this is equal now to our concentration of NO from reaction 3, which is 0.15 to the M power, divided by 0.10 from reaction 1 to the M power. So now we get 2.25 is equal to 1.5 to the M. Go ahead and take the natural log of both sides. So now we have that M times the natural log of 1.5 is equal to the natural log of 2.25. M is equal to the natural log of 2.25 divided by the natural log of 1.5. So 2.25 natural log divided by 1.5 natural log, we get 2. So M is equal to 2. So now we know our first exponent. So now we need to go and find N. So to do that, we're going to basically do the same steps, except this time we need NO to be constant, so it cancels out, and then Cl2 to change, and that is trials 1 and 2. So for this one, now we're going to have the rate of 2 divided by the rate of 1 equals K times NO from 2 to the M times Cl2 from 2 to the N divided by K times NO from 1 to the M times Cl2 from 1 to the N. K's go, NO's go, and now we can start plugging in some numbers. Whoops. The rate of 2 is 0.00450 divided by the rate of 1, 0.00300, and that is equal to our chlorine concentration in 2 is 0.15 to the N divided by 0.10 to the N. So we get 1.5 for our rates divided by each other equals 1.5 to the N. So just looking at that, we can tell that N is equal to 1. All right, take a breath. Now we have our exponents. The last step is to find our K. So eeny, meeny, miny, mo. Let's go ahead and just use our data from trial 1. So now the rate, which is 0.00300, equals K times NO. And NO here is 0.10 to the second power times Cl2, which is 0.10 to the first power. So K is equal to 0.00300 over 0.10 squared times 0.10 to the 1. So that's also 0.10 to the third. 0.300 divided by 0.1. Oops, 0.003 divided by 0.1. 3 divided by 0.1 divided by 0.1 divided by 0.1, and we get 3.0. So now let's look at the units for this for K. The rate is in units of moles per liter per second. So we have moles over liters times seconds, and that is being divided by moles per liter These are squared times another mole per liter. So we can see moles per liter go away. And so then our units now become liters squared on top. And then mole squared is in the denominator, as is seconds. So moles to the -2, seconds to the -1. All right. That was a lot. Sorry, it doesn't fit very well on my page here. This is another really good example for what could potentially be an exam question. So really make sure you guys understand how to do this. Now just a couple more slides for this section. Reaction orders a lot of times are not as pretty as in the examples that we've seen so far. There can be fractional orders and even negative orders. So like I said, my research in grad school, I ended up proposing some fractional orders. I had some 0.75 order and a 0.5 order for reaction. My co-advisor was not happy with the data, but that's what it was. Whereas my advisor was loving it. She liked to create waves. Stoichiometry does not reliably predict reaction order. So you cannot use stoichiometry to do anything with the order of a reaction. Something you have to figure out with data or be told. Only experimentation and data can determine your reaction order. Now the units for the rate constant for K are going to vary depending on your overall reaction order. You have to use dimensional analysis to determine the units and then also go back to check. If you have a zero order reaction, your rate constant tends to be moles per liter per second. For a first order, it's inverse seconds. For a second order, it's liters per mole per second. And for a third order, it's liters squared per mole squared per second. There's some really weird units, I know, but when you go and look and do the dimensional analysis, you see the units cancel out as they're supposed to.